Yeah? Okay. Good afternoon. Finally we can start. Sorry for the delay. We decided that we would always start at 2 o'clock on Fridays and at 2:15 on Tuesday. What we did last time was we went quickly through all classes of optimization problems that I think are important for you to know. And we discovered already that one class of optimization problems is particularly interesting, and these are the so-called convex optimization problems. And what I want to dedicate this next lecture to is to learn a bit more about convex optimization problems, how to check convexity of functions, how to check convexity of sets, and make a connection between derivatives and sub-level sets and so on, so that you can actually find out when you see something if this is convex or not. So the aim of this is that I want to train you, and also the exercise sheet contains a few questions in this direction to discover if something that you just write down like this is a convex constraint or a non-convex constraint. And the reason for this is obviously that convex ones are much nicer, and in the process of modeling, later on, an engineer or a computer scientist or also a mathematician will sometimes have some degrees of freedom of how to model things. And if you get a feeling what is convex and what is not, then you will automatically model it the nice way and avoid a lot of difficulties later. Yeah? So that is why convexity is important. Because we formulate the optimization problems and we can have actually some choice in how to formulate them. But let's at the moment just look at discovering convexity and non-convexity, and this is chapter 3, and chapter 3 is devoted to convex optimization. And the first thing I want to discuss with you is how to check convexity of functions, because that is slightly easier than convexity of sets. You remember when we had a function, we would actually assume that the domain is convex, and then this additional property on the function should hold. I will always assume that the functions we look at are defined on a convex set, and that we know already that this set is convex. Could be all Rn, for example. Yeah? But the first result that I want to discuss with you is something that is related to derivatives. So if you have a function which is a convex function, and this function is also differentiable, so it has actually a gradient everywhere, then it turns out something that we can easily draw. If you would take the Taylor expansion of your function at one point, and the first order Taylor expansion gives you a linear approximation of your function, then this, as you see on this graphic already, is an underestimator of your function. Yeah? So it's a bit funny, because you remember the definition of convexity was that a secant would be above the graph, but now a tangent would be below the graph. That's what we will now prove. And that's actually equivalent to convexity if you have a C1 function. So the theorem says, we call it theorem 3.1. So you assume that you have a function f from some convex domain to R that is continuously differentiable. So it is C1, so 1's continuously differentiable. And of course we assume that omega is convex. So we didn't say anything about convexity of f yet, but then f is convex if and only if. And now the statement is, for any 2 points, so you take one point here, you take another point here on the graph, this point must be above the Taylor series of the other. We call this point here we call x, and this point we call y. And so for all x and y in the domain, this inequality should hold. And how do we formulate this inequality? We say f of y should be bigger or equal to f of x plus the gradient of f of... sorry for writing into my own picture. This is not the best style. I move this to the next line. F of y is bigger or equal to f of x plus the gradient of f at the point x, and then multiplied with the difference of the two y and x. That is the first order Taylor series, and it should be below the graph. This is on the right we have this point, on the left we have that point. Okay? So it's an easy statement to see visually. I want to prove it so that we get a bit used to deal with convex function and also have some time to digest this theorem. So let me prove this in both directions. Yeah. And the first direction is if it's a convex function, then this should hold. This one is relatively fast. So let's go in this direction first. And what we do is actually we use convexity in order to derive an inequality which is actually just a rephrasing of our convexity inequality. I will just write it down. And it says that this f of x plus t y minus x, which was on the one hand, that should have been smaller than f of x at some point, but we moved that already to this side, so we have the f of x on this side, and then the only thing that remains is this distance here of f of y minus f of x. So this was the convexity inequality that we can assume. That was our definition of convexity. This should hold for every x and y and every t which is in the interval from 0 to 1. So for any t in 0 and 1. And now we can use the definition of what is a derivative. So this is actually a directional derivative, so it's very similar to this difference quotient. So when you define what would be this object here, that's a directional derivative of that function in the direction t. Yeah? And so you can also write it down as the limit of t going to 0 from the positive side, but it doesn't matter because it's a differentiable function, of the quotient of f of x plus t y minus x minus f of x divided by t. And now from our inequality here, so that's just the definition of the derivative. And from this inequality, we see that this whole thing will always be smaller than what we have on the right side, t, but it's divided by t, so we know that this is smaller than f of y minus f of x. So we have already proven one side, right? So this thing will be smaller than this, and now we just move this f of x to that side, and we get the inequality that we wanted to show. Okay, so this direction was the fast one. Let's do the other direction as well. And I will do it on the right side of this blackboard. And here we need to go through a slightly different reasoning. What we want to show is the convex inequality, and I will call the point in the middle, I will give it a special name. So I will. So what I want to prove is that the function at this point will be smaller than the linear interpolation, the secant of between a point x and a point y. So I call the point in the middle z. I do a new graph actually. That's maybe easier. So I have this is 3 points. One is in the middle. That is the z. This is the x, and this is the y. And z is actually a point which is x plus t times y minus x. So it's just a shorthand because otherwise I will get crazy. So this is the direction of the proof in the other direction. So from here to there. So we want to show that, maybe I say what I want to show is that, want to show, what do we want? F of z should be smaller than the linear interpolation between f of x and f of z, right? So f of x plus t times fy minus f of x. That's what we want to show. Yeah? So that is this linear interpolation between the two function values, and that's what we want to show. And the only thing that we can assume is this tangent inequality, and of course that the function is differentiable. And what we will actually do is we will use this tangent inequality twice. We will actually make an inequality on this side and one on this side, and then we will add them with different weights. So let me just, so let me state these two things. So what we have here is actually something where we say f of, so due to the assumption on the right side, due to this assumption, we know that the function value of f of x must be above this tangent prediction. So it is actually f of z plus the gradient, this is z, at f at the point z, transpose times x minus z. Okay. The other inequality is f of y is bigger than f of z plus nabla f of z transpose, and here we have y minus z. So these two things are just a double application of this thing. Now we add these two things together, and we add them together with a factor, and the factor that we take is 1. So this is 1 minus t, and here we take t and we add them up. And what we get is an inequality which gets actually the left side on this side. So here we have f of x times 1 minus t plus f of y times t. And on the other side we get, this should be then bigger, then these are two positive factors, so we can just add this. And here we get f of z, here it's one with a minus t, one with a plus t, so it will just still be f of z. And here we get two different expressions, so we get twice the same thing with a z here. So let me just think a moment. This is all correct, I think. But is there anything wrong here? No, should be right.
Would it be a minus?
Yeah, no, I think it's no. There should be a minus. I don't see a minus here. Let's just continue, and I try to add. Let's just collect all terms here. So we have a plus nabla f of z transpose. That's what the same is here. And then we have maybe I collect all terms separately. So for the z here we have a minus t and a plus t. So the term with a t will actually cancel. So we will get a minus z here. I wanted to get rid of the z, so that's why I'm a bit embarrassed at the moment. So strange. Let me just write it down. So until now the reasoning seems to be correct. And I get also what I wanted to have on this side. This is already what I wanted, and now I want to get rid. I want that this is actually 0. And okay, I know what I can do. I will use the fact, I have to use the fact that the z is given by this inequality above. That's the thing that I didn't think of at the moment. Okay, so let us just not replace anything, but this x minus z, we can use here. What is x minus z? Let's make some intermediate computations. X minus z is equal to minus t y minus x, right? So that's from above, and then the same for y minus z is equal to should be so we can also express this with another inequality. We just say 1 minus t x plus t y, and then if we write y minus z, it should be we can actually have the 1. So here we could also say sorry, no. So y minus z should just be the other thing. It's just the other half of this whole thing, right? So this and this. So I think it will just be minus 1 minus t y minus x. But I think we should check this briefly, and maybe it's with a positive sign. I think it is with a positive sign because it's in the other direction. So the 1y is here. So is that equivalent to what we have above there? 1 minus t minus x. There's a minus t. I think this is equivalent, but maybe I should just check that. Do you think this is equivalent to what we have at the top? Just to check you a bit, yeah. But we should be sure that it is right. Intuitively it is, but we can also just look at the. So the y here is just dropping. I get a minus t times y and a minus z, so everything is with a minus sign. And the minus x, is also with a minus sign. So I think this is exactly what we had at the top. And that means that we can actually, the interesting thing is now x minus z gets multiplied with 1 minus t. So this whole thing with 1 minus t. Then here y minus z gets multiplied with t, so this gets multiplied with a t. So then this and this are the same but with opposite signs, and indeed this term will drop. I mean, there will be a lot of terms now, but I just argued why they can be dropped. And then we have it already. So that was a bit ill-prepared, but I think everyone will agree. Okay, so what we have shown is this little theorem that says that the tangents are below the graph. I'd like to state that tangents below graph. That's what we can remember. And from now on, we can just forget the proof. We just trust it, and we have proven it ourselves, and we can be happy. I think I mentioned already the notation that I use quite a lot in this course, namely the one of generalized inequalities. So whenever we have a symmetric matrix, so I just wanted to be sure that we have it. If you have a matrix B in Rn cross n, B being symmetric, then we can write something like this: B bigger than 0 in this curly sense with this matrix inequality that is equivalent to actually for all z, the product of z transpose B z is positive. And that is called a matrix inequality, and it's also equivalent to all eigenvalues of this matrix B are positive, are non-negative. I think we discussed that already, right? I'm not sure, but it feels to me as if I explained that just recently, but it could also have been in another lecture. And we also have the strict version of these things, and so we would just say strict inequality, and then it means for all z that are not equal to 0, z transpose B, z is strictly bigger than 0, and here it means positive. So I will very often use these two shorthands, and I will actually say that these are positive and then semi-definite metrics. So positive definite if it's strictly, and positive semi-definite if it's weakly. So this is just one little definition, and the other definition that we will need from time to time is the little o. But I think you're all familiar with these things. So the big O and the small o, just to be sure. So who is familiar with these definitions? Who is not familiar with them? Then we don't need that, and I will just skip it. Yeah, so this means shrinking as fast as some function, and that means shrinking faster than some function. And we will need that quite often for Taylor series expansions and so on. So what we want now to prove is actually something which is much easier than this to check. So maybe I should say what we want to end with. Until now we have some clumsy definitions of convexity that either involve 2 points and a t, and say for all 2 points and all t's something should be satisfied. And how do you check it? You need to go through all x, all y, and all t, right? Very nasty. There's another thing that we just had. This is only involving y and x, yeah? But still we need to compare it for all pairs of x and y. So when we use second derivatives, we can actually get a condition which allows us to check convexity only with looking at single points. I mean, we will establish a simple condition that a convex function needs to satisfy at every point, but there's only an x. There's no an x and a y and a t or something like this. So it's easier to check. And that's the theorem that we will prove. And it just says it's a necessary and sufficient condition for convexity of C2 functions. And what we will assume is, again, like above, that we have a function f defined on a convex domain, but that it's a C2 function. And omega is convex. So these are our assumptions. And with these assumptions, then f is convex, is a convex function, if and only if for all points in this domain omega, the Hessian matrix, the second derivative of f at all these points, is a positive semi-definite matrix. So that's a statement which is much nicer, I would say, than the previous ones, because you could just compute this by using your usual tools and checking by looking at the equations and proving some things, but you have to check only one inequality for one set of points, namely for all x's, and not for pairs of x and y's. So it's something that is much easier computationally. And what we want to use is actually, we want to use that theorem above, because that will help us here. And let me just go through it in both directions. So first of all, we can already use, I mean, C2 means it's C1 also, so we can apply that theorem above, 3.1. And the theorem 3.1, of that one we will use, this theorem gets the name 3.2. So 3.1, so the condition of 3.1 should imply now the conditions that we have here. So it's the right-hand side which we want to prove. And what we will do here is we look at the Taylor expansion, and we want to prove that the Hessian is actually a positive semi-definite matrix and cannot have a negative eigenvalue. And so for this, we will just look at f of x plus t times p. P here is, you could also think of the difference between y and x or something, but p is a directional vector, t is of course a scalar as usual. So this is given by f of x plus, and now we take the first term of the Taylor series, nabla f of x transpose p. But we also add the second term. So the second Taylor series term is involving the Hessian matrix. And then we have, and it is with t square, sorry. Yeah, so the t must be squared like the p. And the last term is the error term, which is t square p square. So, and this is a little o, so it will shrink faster than t square in particular. And now we can use our inequality, and what we will do is we will first realize that if we bring all these terms to the other side, then we get actually, here we have, so to say, the y minus x. Yeah? So what we know from convexity is that this whole thing, f of x plus tp minus f of x minus t nabla f x transpose p, this whole thing must be bigger than 0 due to convexity. So we can actually bring these terms to the other side. We know this must be bigger than 0, but that is due to the Taylor series the same as 1/2 p transpose nabla f square of x times p t square plus something which is little o of t square. And then we can take the limit by dividing by t square. And so we see that the limit of, I divide this whole thing by t square. X p, and then t squared divided by t squared plus this little o, but this little o will go to 0. So I don't even need to write it down. Huh? So this implies that this whole thing will be positive. And now this holds for every p. This was something I could let hold for every p. So this implies already what we wanted to show. The other direction, let us do that as well. And I think this was based on another variant of this Taylor-Rez formula. So it's always the same way of reasoning. So what did we hear? So now we prove the other direction. So from our new condition, assuming that this holds, we want to show that the already proven direction holds. And here we use, we want to actually show that something is bigger. So we take f of y at one point, and we want to compare it with a Taylor series at f of x. And here we take first order Taylor series at x, y minus x. And then we use the Taylor-Rez term formula, which is, in this case, saying that we can just use 1/2 y minus x transpose, and then the Hessian evaluated at some point which is in between x and y, and I call this point in between, there's a theta. I don't care which theta it is actually, but there is one theta. Which I can evaluate on the line between the two, so that this holds with equality. Now, this theta depends, of course, on y and x, but it exists with theta on the line, theta element in 0 and 1. And so this whole thing is positive because this Hessian matrix is a positive semi-definite thing, and that means that this term here must be smaller than that one. So this implies f of y is bigger than f of x plus this. So we have used Taylor series and definitions of convexity until now. So we have proven this second theorem, and this second theorem I make a box around it because I find it so important. Because it's the main way how we will check convexity of functions when we discover them. I want to go through a few examples, and let's start with the simple ones. So the first one, the exponential function. So let's take f of x being e to the x, compute its first derivative. F prime is e to the x, f prime prime is e to the x, so that's simple, right? And these things, of course, correspond to nabla f and the Hessian f. It's just a one-dimensional function. This is something which is always positive, whatever the value of x is. So we have checked convexity in a computational way now. Okay, so this thing will be always positive. Actually, it will be strictly positive, but we don't need that for convexity, so it will be non-negative. So now for quadratic functions, it's even more trivial, I would say. So let's regard a quadratic function which is something that might have a linear term, C transpose X, like the objective of a quadratic program, plus something which is a quadratic term. And I very often use B for symmetric matrices, which are in quadratic objectives here. So this is a symmetric matrix. It's this matrix that makes this function a quadratic function. And so what would be the gradient? It will be C plus bx, and what will be the second derivative? I think we did that computation already. It will be b exactly. And so you see that this function is convex if and only if the Hessian is a positive definite matrix. So that's actually the reason why these QPs, you remember the discussion from last lecture, were called convex QPs, if the Hessian was a positive definite matrix. So it's what we see here is f is convex if and only if the matrix B is positive semi-definite. Okay? So now another function which is a bit more involved, but I think I still want to share that with you because it's an interesting function. It's a function that is depending on two types of arguments, but I want to check convexity in both arguments together. X is a vector in Rn, and t is a scalar. And so the function is just defined to be x transpose x divided by t. Sometimes called the perspective function, because it's involved when we take perspective images. And so this is on a domain which we define to be omega. That is Rn, that stands for the axis, and then the interval of positive numbers t. So it is not defined for negative or zero values of t, of course, and we cannot divide here. It's a different function, but it's in all x variables it's completely the full space, but in t it's only on the positive half plane. So what we can now do is compute its Hessian matrix, and the Hessian matrix of this function is, of course, a Hessian matrix that is in both variables, x and t. And we can maybe go through it. It's a nice exercise also to first compute the gradient. So what would be the gradient? And I order the variables so that the x is first and then the t. So we will first have here 2 times x divided by t. That's the first part of the components. That's the vector part. And then comes the last thing, which is the t here. And here we have x transpose with a minus sign, x transpose x divided by t square, right? So that is the last component, the last partial derivative here. We can then also compute the second derivative of x and this function. Now please keep in mind that it has these 2 variables, x and t. So this is a vector, this is just a number. And now we go on. So the Hessian matrix is, of course, the derivative of this component with respect to the first. It's just 2 divided by t times the unit matrix. That's what we have here in this block. Here we will have another block, which is the derivative of this whole thing with respect to t, which gives us a minus 2x divided by t squared. Now, if we divide this whole thing, if you take the second derivative with respect to the first variable, we'll get this thing 2x transpose divided by t squared. And we divide this thing, or we differentiate with respect to t squared, and we get plus x transpose x divided by t 3. And I think we get a 2 out of it, right? So we miss the 2 here. So this is the formula that here's a t to the power of 3, right? So that is a Hessian. This is a Hessian that looks not extremely easy, but maybe what we could do first is to make it a bit simpler. We just put this t to the power of 3 out, and the 2 we put out so that it looks a bit nicer, and then what we get here is actually a t squared unit matrix. We get here an x transpose x. We get here a minus t x transpose, and here we get a minus t x. Then it looks already a bit nicer. And what we need to check is now what happens if we multiply this thing with a vector from the left and from the right. And what I take here is a vector that is consisting of a component which is vector valued that I call z, and the scalar component I call s. So if I take this this product here, z, s, I could just take this formula. So I take, I leave the t to the 3 out. And then I can see what I get here. I get several terms, and they get all added up, so it gets a scalar function at the end. Maybe I take first the product of this whole vector with this matrix, and I have actually z divided by s, or not divided by, but here. Then I have my, here I have a t squared times z, that's the first component of this vector, and then I have here minus t s x, and here I have the second component is multiplied now with it's minus t x transpose z, and here I get an plus s times x transpose x, and I do that again. Now with this product, I mean, this is all computations. It's a bit tedious to do it, but anyway, we need to do it. We can still check it. So here we get t squared z transpose z, and then minus t s x transpose z. So that's what we get from this product here. And then we take the product of this with this, and we get minus st x transpose z plus s square x transpose x. And these are all terms, and by looking at them, I claim that these are the same as t, this 2 divided by t3, and then it's actually a vector norm, where we take a vector which is the difference of t times z, so t times z, which comes here squared, and s times x. So if we just take the product of t times z minus s times x and multiply that with itself, tz minus sx. So one is scalar, the other is a vector, then I see that this and this gives this term, right? Then we have the two terms which are this and this is actually the same term, so they appear twice, the mixed terms, and the term sx comes here. So we see that this is actually a product of a vector with itself. So this is 2 times t3 tz minus sx, the 2 norm squared, which is for all positive t a positive number. So it took a while, but by just using normal differentiation rules, things we know, we can now look at this function, and I think you would not easily visualize that this function is convex by just trying to imagine it, right? So you can actually do something here. We can do that for many other functions, but we don't want to do it for all these functions. Of course, what we want to do is rely on others who did these computations already, and just be able to check them if necessary, or if we mistrust them for some reason. Okay? I want to go through a few definitions so that we know what we talk about. So maybe the first definition in this context that we still need to know is what is a concave function. Concavity is actually defined for functions, not for sets. So we can check convexity, we can actually check concavity as well. So F is concave if and only if minus F is convex. So that's more a definition, so I could have had it in the previous lecture, but now we want to do everything convex. So please note that in the definition of a convex function, there was that the function is positively curved, but also that it has a convex domain. So a concave function must also have a convex domain, but it is negatively curved. So in particular, the Hessian matrix of a concave function will be negative semi-definite. So all the eigenvalues will be actually smaller than or equal to 0. Another definition that allows us to actually just talk about convex maximization problems, just so that we know about what we talk about, because very often people maximize, and then you should also not just give up and say, hey, we learned that minimization with convex functions is a convex problem, and then you see a maximization problem. Of course, a maximization problem is convex if the minimization of the negative objective is convex, right? But let us just state maximization problem that you could write like this. Max for some x in Rn, some function f of x subject to some convex constraints in this case. This is a convex maximization problem. We call it a convex maximization problem if if omega is convex and f is concave. So you can easily have maximization problems when you have concave functions, and then they are nice and beautiful, and they are actually convex maximization problems. So it sounds a bit strange that we call it a convex one when the function is concave, but concavity is just convexity with a minus sign. Yeah? I should also note that convexity we could define for both functions and sets. Concavity of sets we cannot really define. So concavity is a nice property like convexity, it's just with a different sign. I think we can go on and try to find out how we can now distinguish convex sets, and how do we see that some sets are convex. And the first thing that I wanted to state is a statement that makes a connection between functions and sets. But before we do it, we start a new section, 3.2. Which sets are convex? That's what we really want to find out. And the first thing, as I said, is a theorem that states something which is also quite easy to prove. But if you have a convex function and you say, I am interested in the set of all points that this function is lower than a certain level, then the set of all these points, the sublevel set, is a convex set. And that's the most obvious way to create convex sets, is by inequalities. Yeah? So the theorem is called 3.3, and says that a sublevel set, which we define by all x in some domain omega, that satisfy that the function f of x is smaller or equal to some level c. Here's the level c. Here's the function f of x. And this set is convex if f from omega to r is convex. So when you take any convex function and you say, I'm interested in the set of all points where this function is smaller than any level, yeah? So this is for any c in R. So you can set this level arbitrarily, and as long as this is a convex function, the sublevel set is a convex set. And this is something that holds independent of the differentiability properties of our functions, so it holds for any convex function. And our way to prove it, and I think it's good that we prove that, we just assume that we have 2 points in the set, so the points in the set are actually from here to here. That's where the set is, so let's assume we have some x and some y in the set. Yeah. And we know that they are in the set, so that means that we have, let me prove it. So we have f of x smaller than c, and we have also f of y smaller than c. And now what we want to prove is that if you take the linear combination of these two things, and you have some point in the middle on the line between them, that then the function value will also be in c, and you see it immediately. Let me just see. So what is the function value at f of x plus t y minus x? So what is this function value? It is smaller because we have a convex function. Then f of x plus t times f of y minus f of x. And that's what we know due to convexity. But now we can actually use the fact that this thing is, actually I will just write this whole thing that we have here in this other form where we have here a 1 and here we have a minus t. So we can just say 1 minus t times f of x plus t times f of y. Yeah, so that's completely equivalent. It's 2 ways to express these convex combinations. But this thing is smaller than c and multiplied with a positive number, and this thing is also smaller than c and multiplied with a positive number. So this thing will be smaller than 1 minus c times, minus t times c plus t times c, which is equal to c. Okay, so we know that the function value itself here, this point, will be smaller than the level c. We see it immediately on this graphic, but this is the proof. So we know that that convex sets can be generated by sublevel sets, and it's enough to know that the function itself is convex. This, I think, is enough for the first hour. The next hour I want to dedicate to operations that preserve convexity of sets. So when you take 2 sets and do something with them, do you get another convex set, yes or no? And that's what we want to do here. Before I continue, is there a question regarding the statements that we derived in this hour? Maybe you can give an indication of the speed, of the level of detail. Yeah? Okay? Still okay? Also, sometimes I could omit proofs. That's something that I did a lot in the last 8 years in Leuven, in front of engineers, I should say. I'm always ready to skip one of the proofs if necessary, but some of them I think are always good to keep for the flavor and also for the for not having the bad feeling that I might just tell you something which might not be true, right? So this is the typical thing. So to summarize, because I want that you are not lost because of all these different proofs, I think the two things that we should really remember are the conditions for convexity, in particular the C2 convexity, positive definiteness of the Hessian, which just means that our function should be having positive curvature. That's a computational thing. And the second thing, please remember that sublevel sets of convex functions are convex sets. These are the two things that are extremely often used, and so you should keep them. But now we have a 10 minutes break. I suggest we start 10 past 3. Okay, we continue. You agree? We continue. So we are still on the way with our journey to prove some useful theorems that allow us to detect if things are convex or not. And for the convex sets, we are still in section 3.2. And we are interested in the question now, if you get a convex set, you know some set is convex, what can you do with this set in order to create another convex set? And there are some operations on convex sets which are actually, you could frame it as a theorem. In the script so far it wasn't a theorem, so I put it in brackets. But these are 3 points actually. If you take an intersection of several convex sets, is convex. And this is not only for finitely many sets, but even for infinitely many sets. Yeah, so I say just sets omega I element in some index set is convex. I can be finite or infinite. And the proof is extremely easy. I think it's still okay to have one visualization of that. And the visualization I do only for 2 sets. But if you're in the intersection and you take a line, then of course the line will be in both of the sets, and so that means that the line will also be in the intersection. And we have proven it. The second and the third property that I want to share with you, they are also easy to prove, but they are, one is called the affine image. The affine image. So if you take a convex set and you map it via an affine map to some other space, then the image of that will also be a convex set. So whenever you take a convex set and you map it through a map which is actually linear plus a constant, so an affine map, then it will be another convex set in another space. Yeah? So what this says is if a set omega, this would be omega, omega is convex. And the affine image is then something that we can denote by A times omega plus B is also convex. This is of course slightly non-standard notation because we apply this linear operator to a set, which just means that we apply it to every element in that set. And a cleaner definition of this whole thing, of this here, is that we say it's the set of all y's in the output space. So let's say Rm. Here A is a matrix which maps from Rm to Rn. So this is the set for all y's, so that there exists an x in omega, so that y is equal to ax plus b. Extremely tedious to write, even. I think this, but it's the same as this. So maybe just adopt this notation and then you'll remember what it means when necessary. Also, this is quite clear because an affine map, it's a linear map, so a linear map plus a constant will preserve lines. So whenever you have a line in one space, after an affine transformation, it will remain a line segment, and so line segments remain in the set. So if an image is quite useful, if you, for example, think of the projection of a set, that's nothing than taking away one component, but it can be expressed as the multiplication with the matrix. Yeah? So affine image is something of the operations which are very useful and also quite straightforward. And then there is the other, the contrary of this is actually if you start with a convex set and you have an affine map into that set, then the points of the set of points which are in that in the pre-image, that is also a convex set. So this is a theorem that we call affine pre-image. So we have the same map here, AX plus B. The matrix, just defines, we could define the dimensions the other way around, so that this is still in Rn, our starting space. And then what is the pre-image? It is the set of all Z, so that A times Z plus B is element in omega. Is convex if omega is convex. So what we got here is that affine maps connect convex sets with each other. Yeah, so on one side of this you have a convex set, then on the other side of the map there will also be a convex set. So this is extremely nice. So affine maps will not change convexity of sets at all. Extremely powerful and useful. I want to give a few examples for convex sets, because we can have myriads of examples, and I encourage you to just, whenever you see a set or maybe a form or a body, think, is it convex or not? That's good training. Huh? So just, for example, if you see a cube, is it convex or not? Yes. Yes. Is a ball convex or not? A banana? No? Okay, yeah. So, but of course in mathematics, and particularly in optimization, we are really interested in sets that are described by inequalities. And so let's make something that's relatively general and which we will use a lot in optimization. And this is a convex feasible set, I call it, because it uses the same notation that we used before. And I regard functions if fi from, and I say from Rn to R, and I is going from 1 to, let's say, m, are convex. Yeah, then the feasible set that we will define, then omega, that I define to be the set of all points in Rn, which satisfy fi of x being smaller than 0, for I from 1 to n is convex. And this is quite easy to prove. Why? Because we could define sublevel sets. So let's define a sublevel set for each of these functions. So we have f of I x smaller than 0. I is not for all, but yet just one. Is convex, is sublevel set of a convex function, right? So it is convex for all the indices I. And now omega is of course the intersection from I1 to m of all the sets omega I. So we see that directly by applying two of our theorems, sublevel sets and intersection, we can see that this is a convex set. So that's quite remarkable. It means that when we have convex functions and they appear on the left side of a smaller or equal sign, on the smaller side, then it implies that we have a convex feasible set. I want to give you another example just to open your mind and to make you sweat a bit. Okay, so another convex set which is not something that we usually think of are the so-called the sets described by linear matrix inequalities. Linear matrix inequalities. And I just say that they are abbreviated LMI, and they stand for the LMI in YALMAP. There is a YALMAP. Yeah? So just here's an LMI. And that's on purpose because YALMAP was originally invented as a modeling language for linear matrix inequalities, which I will introduce now. And it said yet another linear matrix inequality parser. And nowadays it's much more powerful, it does everything, but still in the names some artifacts are still present which come due to the history that it started as an LMI tool. So the first thing is I want to define a convex set, and I want to define a convex set with help of another convex set and with the help of an affine map. And the first convex set I will introduce is actually the set of all positive semi-definite matrices. That turns out to be a convex set. So the first thing is let me define a space. Yeah. So the space of symmetric matrices Sn, I think the index we give at the top side. Sn is the set of all matrices X in Rn cross n, so they are square matrices which are symmetric. Transpose. Yeah? So that's an easy set, and there is an easy way to represent it. If you think of what is a symmetric matrix, it's a matrix where all the elements that really matter on the top part, and then these are, and on the diagonal, and these are the same elements. So it is actually a dimension, a space, a vector space of a dimension that is n times n plus 1 divided by 2. So that's the dimension of this space. This is the number of numbers that you need to represent one element. Yeah, so this is just a vector space. It's equivalent to Rn times n plus 1 half. Yeah, so this is all fine, and now I claim, I mean it's a space, so obviously this is a convex set, right? But what I claim is that the subset of positive semi-definite matrices is convex. So the set of positive semi-definite matrices, which is, we could call it Sn plus, which is just the set of all x. X is, maybe I should use a big X, so this should be a capital letter just so that we get this feeling this is a matrix. For all the matrices which are symmetric and which have the property that X is a positive semi-definite matrix. So this set is convex. And that's something I just state, but we can easily prove it by using our statements from before. And to prove that this is a convex set, I want to use the definition of positive semi-definiteness that we introduced just before by saying for each z that we multiply from left and right to a matrix, the product must be positive. Huh? So we actually can say that this thing holds, right? If and only if for all z in Rn we have that z transpose x is z is positive. That was the definition. But what is this in terms of inequalities regarding the variable x? It is for each fixed z, this is actually a linear inequality on x. A linear inequality, I didn't say that, but it's implied by our sublevel set theorem. If you have a linear function, it is convex and concave. Linear functions are the nice things, right? Linear functions are convex and concave at the same time. So also the negative thing is convex. So the sign doesn't matter. If you have a linear map on any side of an inequality, it will always describe a convex set, a linear scalar. And this is a linear scalar map on the variable x for a fixed z. So what we can actually say is that this set S of n plus is nothing else than the intersection over all z in Rn of the sets which are described by x in Sn, which satisfy that z transpose x z is bigger than 0. And for each fixed z, we easily see that this is a convex set. It's actually a half space, because this is just one equality which says that something of this x should be, some linear function of x should be positive, so it's cutting away half the space in this high-dimensional interesting space of symmetric matrices. And then we intersect infinitely many of them for all z. So you see it is a convex set because it's the intersection of convex sets. It's actually the intersection of half spaces, of infinitely many half spaces. Okay, so we have now we have a convex set, and this is not yet what we call a linear matrix inequality because it's just one set which turns out to be a convex set in a high-dimensional metric space. But now we want to actually define convex sets in a normal real Rn or Rm we call it here. And in order to do that, we will actually have a linear map that maps from Rm into this metric space. Yeah? So the first ingredient was that we have already a convex set here. This Sn plus, yeah, that's a convex set. I hope you agree that this is a convex set. If not, we can actually argue a bit longer. Okay. I didn't introduce half spaces before, but half spaces are actually parts of space where you just go through zero with so you take your space, you cut away the half of it, and the other half is then what we call a half space. And cutting away means you include one linear inequality. Okay, but now the second ingredient will be a function g, which maps from Rn to Rm to the space of these symmetric matrices in Sn. And it will be an affine map. So it will be that g of x is equal to this sum of a0 plus a sum of ai times xi, I going from 1 to m. With all these matrices a0 up to am, they should be symmetric. So if you take a lot of symmetric matrices and you weigh One is just additive, that's the affine part, and these are the linear parts. Each of them weighted with some real number, x. This is just the component of the vector x. Maybe I should just make this clear. X is just a vector consisting of real numbers up to xm. So that's the set we are interested in. We have a linear map, an affine map, sorry. It's a constant plus a linear, so that's an affine map. And if all these matrices are symmetric, then of course the matrix G will also be symmetric, so we really have a map from the Rm to the symmetric matrices. And now we could define the set of all x in Rm so that G of x is a positive. Or equivalently, that G of x is element is in Sn plus. And what do we get? We get the pre-image of a convex set under this affine map. This is convex because it is the pre-image of a convex pre-image of Sn plus under G. And G was affine. So I should maybe say this is an affine map. So this inequality here that we have, or I can also write it. If you write something like this form, a0 plus sum I equals 1 to m ai times xi bigger than 0, this is called a linear matrix inequality. So this strange object can be written down. It is using positive semi-definiteness in a completely different context than what we did before. We used positive definiteness before just to prove convexity and such things. Here it is defining a convex set. It's not something that a function should have or something. It's actually the inequality that replaces other ways to define convex sets. And so we have a new example of a convex set which is quite different from the standard way that we have that we usually deal with in this course also. Yes? Usually we look at differentiable functions from Rn to Rm or such things, and here we look into this metric space. So we will come back to that. The remark already, optimization problems with LMIs as constraints, they are called semi-definite programs. Just a name that we should not get confusing. I mean, LMIs and semi-definite programs come together. So like linear programs come together with linear constraints. But before we come to this class, I want to go through some operations which preserve convexity of functions. So again, we looked at functions, we looked at sets, we looked at ways how to preserve convexity of sets, and now we come back to functions. So are there some operations that preserve convexity of functions? And this is something quite relevant, and I just want to tell you one example where you use not convexity but some properties that you know that functions have quite often in your daily life. So when you have two functions and you know both of them are differentiable, then for example the sum of the two will also be a differentiable function. You know it. Yeah? You don't have to go through some proofs or something. Also, when you take one differentiable function and you plug it into the other, this will be still a differentiable function. Yeah? And so these properties are quite easy and understandable, and actually we are all trained in it for differentiable functions. We are not so well trained in it for convex functions, but actually there are people that are extremely well trained in detecting convexity of functions with similar rules. But the rules are a little bit different, and three of these rules I want to give you already, so that we get a flavor of how you can detect convexity of functions by just looking at them and seeing some things. Yeah? I think I add some things, because otherwise we forget them. So which operations preserve convexity of functions? The first one I want to already state, because it's something I forgot. Sum of convex functions is of course a convex function, right? If you sum two of them up, or several of them, and more general, you can have also a positively weighted sum. Yeah, so you just take convex functions, you multiply each of them with a convex number, with a positive number, and you add them up, then you have a convex function. A second thing is a bit more subtle, and that is an affine input transformation. But it's something which is also extremely useful and nice and easy. So if you take some function which is convex, f from omega to r convex, yeah, then you can also take a function which is f of a times x plus b, where a should have, of course, the right dimension to map into the space in which omega is embedded. So if this is convex, then this function is also convex. Yeah. To be specific, actually, we would have to define a new function. Maybe we call this whole thing f tilde of x. And then this new function, f tilde of x, is a function that maps from omega tilde into r. And omega tilde should, of course, be the set of all points where this affine map maps into the set of definition of our convex function. So it is the set of all points x, so that ax plus b is element in omega, which is the affine pre-image. So this omega doesn't look like an omega, sorry. This is an omega. So this omega, if this function is convex, omega is convex, this is a pre-image, so then omega tilde is also convex. So the domain of this function is convex, and it's also easy to prove that this function itself is convex. So I will not do it. I can also, it's okay like this. Affine input transformation. So basically, if you take a convex function and you change the basis of the domain, for example, you just rotate the space in which you are by linear transformation, you will end up with another convex function. As one example. There is another thing. So this is something you just have a convex function and you plug into an arbitrary affine function. This will always give you a convex function. But now there is another thing. When you have, for example, differentiable functions, you plug one into the other and you have another differentiable function. So would this also be the case for convex functions? And of course it would be very nice, but unfortunately it's not the case. So if you take one convex function, you plug it into another one, it's not necessarily a convex function. But one can actually find one special case it's one extra condition that you need to put on one of the two functions, and then the concatenation of two convex functions is indeed convex. And this extra condition is that the outer function must be monotonely non-increasing. So the second statement is the concatenation with a monotone convex function. With monotone convex function. And so what we do here is we take two functions, and one is the inner one. If f from omega to r, and omega can be any domain, and g from r to r are convex, so if these two functions are convex, g will be the outer function because it's just from r to r, so we can apply it to the output of function f. And if this outer function is monotone, and if g is monotonely non-decreasing, non-decreasing means, I think in the script I wrote increasing, that is wrong. So it must be monotonely non-decreasing, which is slightly weaker. It's not wrong actually in the script, but it's just, it can be strengthened by making it this expression. Then, if these two things are satisfied, then the function g of f of x is convex. So I'm just plugging in the f into the g. And the proof for this can be done in different ways. I actually decided to make a draft proof for this only. That means I prove it only for the case that we have differentiable functions as well. But the statement holds in general, I should say. So it's not a statement that is limited to differentiable functions, but it is easier, quicker to prove it. So I do it only for that case. What I will do now is I will just take the derivative of our concatenation and then check its second derivative, that the Hessian is a positive semi-definite matrix. So let's do it. So we have the function g concatenated with f. That's the function that we are interested in. And if we take the gradient of that, and apply it to some point x, then it is, of course, the, let's first do the outer derivative, then we have g prime of f of x times the inner derivative nabla f of x. And that's it. So now, if we take the second derivative of this whole thing, then it's getting a bit more messy. So we first regard the first term and then the second term. If we regard the first term, we will get a second derivative here. I keep that with the usual primes because it's a scalar function. And I get the gradient out of that. And it turns out that the other gradient is still there. I need to transpose one of them to make it a matrix of the right dimensions. So if I would do it index-wise, this would be exactly easy, but this is a number, this is a standing vector, that's another standing vector. And now I take the second derivative of this thing, but that is easy. So here I have g prime of f of x times the second derivative of this thing is just the second derivative, so directly Hessian matrix. And now we made our assumptions, and as I said, I will prove it under the assumption that both functions are twice differentiable and convex, and one is monotone. So this thing will be, because of convexity of G, positive, right? This thing is the outer product of two vectors. It is by definition a positive semi-definite matrix. So when you multiply from left and right any vector to it, it will be 2 times the same, so it will be a square of something. This thing, also due to convexity, will be a positive semi-definite matrix. Otherwise, the second derivative wouldn't be positive. Otherwise, this could not be a convex function, right? And now the only remaining thing that we would also like to be positive, so that everything here is a positive addition of two positive semi-definite matrices, which is of course positive again, is this term. And this is positive due to the it's non-negative due to the non-decreasing property of our function g. So it's a function that has a zero or positive derivative, but it can never go down. Yeah? So this is convexity. This is just a property. This is also convexity. And here is the non-decreasing. Yeah, so this was convexity of G, convexity of F, and non-decreasing of G. And this was a general property that any function would have. And so then we see that due to this, we have positive semi-definiteness. Two positive semi-definite matrices added to each other give a positive semi-definite matrix, and we have what we wanted to show. So this is a partial proof only, I should say, of the theorem, because we proved it under the condition that the two functions would be C2. But you can prove it also more general, and we can do it if you like in an exercise at some point. The next thing I also wanted to share with you is the supremum of several convex functions. So if you take a collection of convex functions, you don't add them, but you actually take the maximum or the supremum of them pointwise. Then it turns out to be also a convex function. And that's quite a remarkable and also very useful property. So this is the 3 supremum, or if it exists, a maximum over set of convex functions. So maybe I should first illustrate it with a graphic. So imagine you have one convex function and you have another convex function. Then the maximum of these two convex functions is the function that I have here. Right? And you immediately see from this graph, okay, that seems to be a convex function as well. Right? It has a kink, maybe not differentiable anymore, but convexity is something independent of differentiability properties. And so this thing is easy. So f of x, the supremum of all I in some index set I of function f of I, fi of x with some so this is fi, this would be fj, and this would be x. And we take the pointwise supremum. Here, this function is the maximum, for example. So this function here is convex if fi are convex for all I in the index set I. And again, this index set can be finite or infinite. And the proof is extremely powerful application of our characterization of convex functions. At some point I said, what is a convex function? A convex function is a function whose epigraph is a convex set. The epigraph is the set of points above the graph. So if we take this picture, we see that actually the maximum of two functions is the intersection of the epigraph of the maximum of two functions is actually the intersection of the two epigraphs. So take this epigraph, take that epigraph, intersect them, and you get this set. And that is the epigraph of the supremums function. So it is an easy application of the epigraph formulation. It's the intersection of convex epigraphs. That's what will help us here. I think I want to conclude with a statement that allows us to recognize immediately that an optimization problem is convex. And this is the following. You remember so the standard form, you remember we had one standard form before where we just said minimize f of x, x in Rn, subject to g of x are equal to 0 and h of x are bigger than 0. So that was one statement, quite general, of an optimization problem. And now we see from what we had before that this is there is a sufficient condition for this to be convex, and the condition of must be that this f is a convex function, that these h, they are on the wrong side of the inequality, so there should be actually concave functions, each of them. And then we have the equalities, and it turns out that if we have nonlinear equalities, they will in general lead to a non-convex set. Yeah? So the level sets of some nonlinear functions are usually some curved sets, and curved sets are not admitting any convexity. So this is convex if, so it's a sufficient condition, f is convex, h, I are concave, each of them single, and G must be affine. So the only thing that G can be is actually a linear map. It cannot be curved. And why? Because then this point 0 is actually 1 point. 1 point is a convex set, and the set of all points where an affine map maps to this 1 point is a convex set because it's an affine pre-image of this convex set. So another form that people actually like to state convex optimization problems, and that you find also in some textbooks, and that's why I stated here, is that you say, actually I could also directly write it this way, that I say, okay, I know this is affine, so I don't have inequalities apart from matrix inequalities, which I can easily write down this way, and then I make all my inequalities smaller than 0, so I just turn them around, where I goes from 1 to m, and then I write this thing already in this form, which is a bit reordered, and then I could say this is convex if f0 up to fm are convex. So that's a nice abbreviation. Note that the objective gets the index 0, and then I start with the inequalities starting at 1. So all these functions should be convex, and of course here can be some linear equalities, and then everything is a convex problem. So that's a sufficient condition. Here it was already a sufficient condition. for convex problems. And I should say that usually if an optimization problem is not in this form and has some non-convex functions here, it might still have, in some exceptional cases, a convex feasible set, but it's extremely difficult to prove that. So it's actually the most useful definition of a convex optimization problem. Apart from those, I should say that involve linear matrix inequalities, which are a bit out of this framework. I want to give you one example of a quite interesting class of optimization problems which have this form, and that is what we call a quadratically constrained quadratic program. QP, and this is abbreviated QCQP. And here we will have actually the functions fi of x are just given by di plus ci transpose x plus 1/2 x transpose, and then we have these matrices b I x. So these are symmetric matrices, which should be positive definite, semi-definite, bi 4, I going from 0 to m. So if you have an optimization problem with some variables x, which have only linear equalities, and which have a quadratic objective, this is a quadratic objective, of course, quadratic plus linear plus constant, and which have only quadratic inequalities where this fi is on the left side, so smaller than 0, then these sets actually describe some things like ellipsoids or hyperboloids, paraboloids. So these are actually nice objects which are always convex as long as the matrix bi is convex, because the second derivative of this function is positive semi-definite. That means that it is a convex function. That means that all these functions are convex, and then we have a convex optimization problem. So QCQPs, I think, are a nice example of an optimization problem which is a bit more general than what we have known already, LP, QP. It's more general than a QP. And these are also problems which are easily solvable and sometimes appear in applications. Next time, we will go on a bit with convex optimization and state some optimality conditions, and also look into SDPs again. And then we will introduce the Lagrangian function and duality, which is the last chapter of this basics and foundations part. We'll be a bit involved again. And then after that, we start the next part, which is really about algorithmic solution of problems. And then we will go a bit less theoretical again and more algorithmic, and I think also a bit shallower from the mathematical side. Yeah? But still, we are at the foundations part, and I think these are foundations I want to share with you so that you know what is a convex problem, what are these names of problems, and what are optimality conditions. So we will continue a bit on this theoretical side next time. Thank you very much, and have a nice weekend.